Welcome back, students. In this session, we will look at the concepts of another deep learning model called as deep belief networks. It is a composition of stack of unsupervised networks. Similar to autoencoders, this is also runs on unsupervised methodology. It is exactly similar to the restricted Boltzmann machine, which we have already learned. As you have already know that RBM will have a visible input layer and also a hidden. It's treated as a single layer architecture with one input and one output layer. Now what happens in deep belief network is it is a stack of RBM. So you have one RBM in the input stage, then you have the second RBM stacked with each other. That means the output layer of the first RBM will act as an input layer for the second RBM. So when you consider the stack of two RBMs, you will find one input layer, one output layer, and one hidden layer. That hidden layer will act as both output layer and also an input layer. So it is a virtual connection. It's not a physical connection. So you can say that DBN has connections within RBM and not between RBMs. Again, the original training data is represented in variety of ways. Mostly it will be available in the form of in the compressed form or in the form of a reduced data. You can say that only the important features are extracted from the input data, or otherwise you can say these layers, initial layers, are doing the process of feature extraction. So when you have multiple RBMs, you can say that there are many feature extraction procedures which are going to take the necessary data. And the algorithm we use is greedy algorithm, as we have seen in the different optimization methods. So this is the diagram. You can see the green color as the input layer and the red color as the output layer. And you can see the neurons too. And now you can see RBM1, 2, and 3. So when you say RBM1, one input layer and one output layer. That output layer is called as hidden layer 1 in the deep belief network. The same layer will act as an input layer for RBM2. So it's only a virtual connection, and likewise you can have different number of RBMs which are going to do the process of feature extraction. Here is the zoomed up version of one RBM where you will have a visible unit and also a hidden unit, or you can say an input layer and an output layer. Again, this can be used for classification depending upon the process which we have already learned. You can use it in whatever way you need. The third model which we are going to see is the long short-term memory network, or in short it is called as LSTM. Already we have learned the concepts of recurrent neural network, or RNN, which is used to predict the future data with the help of the already stored history of data. And predominantly these type of deep learning methods are useful for continuous time series data such as your signal and text. This is an example for RNN. So one can easily say that the past history of data is stored, and based on that we are going to take a decision. But now the question is, how much past history need to be stored? Should I store for 1 day, 1 week, 1 month, or 1 year? RNN says it can store only a limited set of data, or otherwise the storing capacity is very much limited. Suppose if you are forced to take a decision on a future data based on the previous year's data, then it will not be possible with RNN. If it requires a long memory, then it fails. To solve this problem, we are going for LSTM. In other words, RNN is incapable of long-term dependencies, whereas your LSTM is capable of long-term dependencies. So it has architecture-wise, it has a chain of repeating modules. You can see the three square boxes here. On the left and the right, you are going to have the same structure as you have in the middle part. So what we are going to have in the middle part? The basic one is the line C, which is going to take the previous data to the current data, which we call it as a cell state. So this cell state changes from t minus 1 to t, where t is the number of iterations, and the data flow is via 3 gates. The first gate is called as forget gate layer, where you have a sigmoidal activation function. We already learned that your sigmoidal activation function can give an output of 1 or 0. Now, if you closely observe, this output is going to get multiplied with the data in the cell state. So, when you have an output of 0 from sigmoidal activation function, the overall output is going to be 0 because anything multiplied with 0 is 0. In that way, you can say that the data is removed from the history. Not all the data which you store is essential for your operation. In the same way, when you have a sigmoidal value of 1, then that data will be retained. The second layer put together is the input layer. Now we have the data to be available for the decision making. But the question is, do we need to make any update on the data? If yes, what new addition are we going to make? For that, we have a combination of sigmoidal activation function and tangential hyperbolic activation function. So tan H output, we know already it will be +1 or -1. So when you have a -1 output, the data is going to be reduced. When you convert your text data in the form of numbers, you can easily have a reduction in the number. The same way, when your tangential hyperbolic function is 1, it is going to be added. In that way, you can make an update in the overall output. And the last layer is the output layer, where all sigmoidal, tangential, and your H function are coming into place, where you can see the mathematical equations from the previous layer we take and we just convolve with our original output. When you have that convolution, you can say that the history of data is obtained for the next layer, and at the same time you can have the OT and the CT values also. So this process will be continued one by one depending upon the number of chain modules you have. The longer the modules you have, better will be the decision making process. Thank you.